Last lecture we had started discussing about this topic, series and parallel operation of thyristors. So rather than revising what we discussed last time, I'll take the topic ahead today. So there will be some circuit diagrams and some tree associated. So I'll be writing it on the board. Yeah. So we studied that there are certain applications in the field of power electronics which need high voltage and low current, while some others need low voltage and current. So we have discussed that if the DC or AC voltages to be blocked are greater than the breakover voltage of a single SCR, then we connect two or more SCRs in series. On the other hand, if in a particular application the current to be conducted is larger than the current carrying capacity of an individual SCR, either it is RMS or average, then we connect SCRs in parallel. But we told that connecting SCRs in series or in parallel is not as simple as it appears to be, but there are certain problems associated with series connection of SCRs and parallel connection of SCRs, and how to overcome or minimize those issues. We need some solutions that we are going to discuss today. So we already discussed last time by taking an example of an AC voltage controller. In an AC voltage controller, what is expected is that VLAVC in voltage should be 0, but it is possible only if the two SCRs T1 and T2, which are connected in anti-parallel fashion, are exactly identical. But in semiconductor devices, even if the part numbers are same, even slight variation in the fabrication steps will lead to an appreciable change in the datasheet parameters, leading to an inequality operation. We discussed that thing. So similarly, certain issues during these parallel connections, which are as follows. Series operation or series connection. When SCRs are connected in series, they should belong to the same class and should have exactly identical second important point is practical The following important parameters do show certain amount of equality, namely blocking voltage or breakover voltage, junction capacitance, so what we are referring to is CJ1, CJ2, CJ3. Third is delay times, T. Fourth is V on, and reverse recovery time. Which is denoted as TRR. Okay. Okay. So whatever we have mentioned in point number 3, it leads to, sorry, whatever we have mentioned in point number 2, it leads to the following consequence mentioned in point number 3. So we can say due to the above inequalities, the following problems arise. The first is unequal distribution of voltages across devices. Unequal distribution of the input voltage across devices. Okay, obviously the device is connected in series. Second is difference in reverse recovery characteristics. Okay. So in order to solve the problems which are mentioned in point number 3, what we have to use is called as voltage equalizing network. So we can say to overcome or minimize the above two problems, we use voltage equalizing networks. So the solution which is mentioned in point number 4, how does it solve the problem? It solves the problem in the following way. Okay. So voltage equalizing network forces equal sharing of input voltage across the series SCRs. Okay. So voltage equalizing network forces equal sharing of input voltage across series SCRs. Okay. So now these voltage equalizing networks are of two types: static equalizing network and dynamic equalizing network. There are two types of voltage equalizing networks. So we can also abbreviate it as VEN. Okay, when there are two types of voltage equalizing networks, namely static voltage equalizing network, and second is dynamic voltage equalizing network. So we'll draw the diagram directly. So we can say point number 7, consider a series connection of two SCRs as shown below. So we have the first SCR and in series with this we have the second SCR, its terminals. Okay. So now we have anode, cathode, gate, anode, cathode and gate. So to the right I will draw a static equalizing network, and to the left we will draw a dynamic equalizing network. Both resistors have a value of R ohm. This is static VEN, and to the left we have the dynamic VEN. Diode D or CNC. And we have exactly similar network on lower SCR. Static VEN, okay, so we can just put a note here. The values of R in static voltage equalizing network and the values of RC, C and D in dynamic VEN are designed so as to force equal voltage distribution across the SCRs T1 and T2. So let us say that this is T1 and this is T2. Okay, so when we say dynamic VN, we can put a note here that this refers to when input is AC, and static VEN we can say when input is DC. The eighth important point is during transient conditions, unequal voltage distribution occurs in terms of turn off, turn on, and high frequency operation. And all these are because of so in this particular circuit diagram, this capacitance C, they will lead to equal voltage distributions to compensate for inequality in the junction capacitances. Okay. The mismatch between SCRs is compensated by the shunt capacitance C. Okay. So this was all about how to solve the problem of unequal voltage distribution in series operation. Now we go on to parallel operation or connection of SCRs. So SCRs are needed to be connected in parallel when the circuit current exceeds the current rating of a single SCR. Circuit current exceeds the current rating of single SCR. Again, similar to the terms and conditions needed for series operation in order to have equal distribution of input voltage across the SCRs, here also they need to be identical. So SCRs connected in parallel must be exactly identical. Okay. Consider two SCRs connected in parallel as shown below. So we have the first SCR T1 and we have the second SCR T2. Anode, cathode, gate, anode, cathode and gate connected in parallel. Okay. And we have some current I which exceeds the current rating of a single SCR, and if you want to conduct this, then it can be divided into two parts by having it flow through two SCRs connected in parallel. Okay, so here I will get divided as I1 and I2, and it will ultimately return. Okay, now I1 will be equal to I2, I1 will be equal to I2 will be equal to I by 2 only if T1 and T2 are exactly identical. Okay. Now take a practical example where I want to control an RMS current of 20 amperes. Now a single SCR T1 612 has RMS max rating of 12 amperes. So this 20 amperes current, if it flows through a single SCR, it will damage the SCR. So what we do is that I connect two T1 612 devices in parallel, and if both are exactly identical, each of them will carry 20 amperes by 2 equal to 10 amperes of RMS current. Okay. So now if this is 20 amperes, then I1 will be 10 amperes, 10 amperes if T1 is exactly equal to T2, identical, not equal to. Okay, so we have 20 amperes here, 10 amperes here, and 10 amperes here. So what are the different reasons because of which the current I1 will not be equal to I2 equal to 10 amperes? It's here. Rather than in differences, we can say inequalities. Inequality between the on state, that is V on values of the parallel SCRs results in unequal distribution of circuit current through individual SCRs, right? So the reason between unequal distribution of circuit current through individual SCRs is the inequality between the on-state voltage drops of the parallel SCRs, even if they are having the same part number. Okay. Now this inequality between V on leading to unequal distribution, what does it ultimately lead to? It leads to thermal runaway. Okay. So unequal distribution of the input current leads to thermal runaway of the SCRs. So basically, thermal runaway will ultimately lead to destruction of SCRs. Okay. So rather than writing this, we can say thermal runaway. It leads to increase in the junction temperatures and this leads to the junction temperature Tj exceeding what is called as Tj max, and this basically leads to the power dissipation across the device exceeding the maximum power dissipation limit, and ultimately it leads to destruction of the device. Okay, so it's like this. So what is the solution to this? The solution is given for two different circuits. One is AC circuit and one is DC circuit. To overcome or minimize the problems mentioned above, we have two different solutions depending upon what is the type of input. So whether it is DC, whether it is AC. Okay. Okay. So for DC circuits, so we should not forget that what we want to achieve. What we want to achieve is equal sharing of currents through the parallel SCRs. For DC circuits, anode, cathode, gate, anode, cathode and gate. Okay. So we just introduce two resistors in series with the SCRs in this way. The current I1 flowing through the SCR T1, I2 flowing through SCR T2. So we have T1, we have T2. Okay. You can say here so R1 comma R2, they help in equal sharing of input current I. So for AC circuits, equal sharing of input current I in AC circuits is enabled by using a reactor. Magnetic coupling of parallel current paths makes the current sharing more uniform, equal. Okay. Say magnetic coupling of parallel current paths makes the current sharing more uniform or equal. So again we consider two SCRs T1 and T2 connected in parallel. So from here comes our AC current. I. anode, cathode, gate, anode, cathode, gate. AC. Just like R1 and R2 are helpful in equal sharing of input current I DC, so we can also write here that L1 comma L2 So this was all about series and parallel operation of SCRs. Okay.